So I know story problems are the bane of many students' existences, and I think I know why. I feel as though when you first learn how to do story problems, there's a real emphasis on trying to do them quickly. It's a bit like math is going to the dentist or something. You just want the appointment to be over as soon as possible, and it doesn't matter how much the dentist screws up your teeth as long as it's done. So I think that does story problems a disservice. After all, life is a story problem in a lot of respects. And so my advice in working a story problem is not to put too much pressure on yourself to jump straight to the answer. Specifically, students often put too much pressure on themselves to jump straight from the verbal description of a problem into an algebraic equation, which they can use to model that problem. And that step is not one that you can or should be expected to take in one fell swoop. So in this particular story problem, the information that we're given is about the amount of credit on a phone card, which I don't even know if phone cards exist anymore, at least in the US. And we want to turn that information into a prediction about what's going to happen if there's 92 minutes of calls on the phone card. And so when an algebra teacher looks at this, they say, oh, just write an equation for this and then use the equation to make that prediction. But that really does a disservice to the process of writing that equation in the first place. And that's the process I want to focus on in our solution. So here's the strategy. The first thing we need to do is to figure out what kind of information about this relationship between calling time and remaining credits has been given to us in the problem. And once we know what information is given to us, we can then use that information to find a linear equation. And then use that linear equation to make a prediction, which is what's being asked for here. What's the remaining credit after 92 minutes of calls? So at this point, we kind of have a sense of the different ways in which linear equations are described for us. We know, for example, that if we know a slope and if we know an intercept, so if we're given these two things, then we know what to do with those, right? We can just plug the slope right into the M and the intercept directly into the B, and we'll be done. But it's very rare in the wild that somebody comes up to you and hands you a slope or hands you an intercept. That's just not something that happens very often. So conversely, what if somebody gives us a slope and not the intercept necessarily, but just some other random point? Well, we also know what to do with that. We can use the point-slope form of a linear equation. Plug the slope in there for M, plug the x and y coordinates of the point in there for x1 and y1, and then we can be done. Which happens a little bit more often, but still not very, right? Because it's also a very rare occurrence that somebody hands you the slope of a linear relationship, and this story problem is no exception to that. So the other example that we had was what to do when what we have is just 2 points. So we're not given a slope, we're just given the coordinates of 2 points on this line. And we knew what to do in the last example with this. We had to find the slope. And that was step 1. And then we can use that slope along with one of the points that we were given in our point-slope formalism to get an equation for the line. And because that's the situation that happens far more frequently in reality to determine a linear relationship, that's going to be the strategy we take for this problem. Okay, so let's flesh that strategy out. So the verbal description here says that the credit remaining on a phone card is a linear function of the total calling time. Right off the bat, the information that's giving us is it's setting up a relationship between two numerical quantities. On the one hand, the credit remaining on a phone card, and on the other hand, the total calling time made with the card. We also have units, dollars and minutes. And in a sentence where it says blank is a function of blank, that sets up the independent and dependent variable in a particular order. Specifically, it sets up that first quantity as the dependent variable, because they're saying it is a function of something, and sets up the second quantity as our independent variable. So if we're thinking about x's and y's in Cartesian coordinates, let's just try to keep things simple on ourselves and do that. Then that's setting up the credit remaining on the phone card as our y coordinate, our dependent variable, and the total calling time as the independent, the x, the horizontal coordinate. That's also suggested to us by the graph that's provided for us in this problem. Calling time is on the horizontal axis, credit is on the vertical axis. So we think of calling time as our x and credit remaining as our y. Okay, great. So we know that x is going to represent the total calling time, y is going to represent the credit remaining, and they're telling us that the relationship between these two quantities is modeled by a linear function, a linear relationship. All right, so what information do we have after that that tells us something specific about this relationship? Let's look at what we have. The next sentence says, the remaining credit after 38 minutes of calls is $23.92. Well, we decided that the total calling time was our value for x, and the credit remaining was our values for y. So this sets up that somewhere along this relationship, we have a place where x is equal to 38 minutes of calls, and y is equal to 23.92, $23.92. So that's giving us a point on this line, whose x-coordinate is 38, and his y-coordinate is 23.92. So we've just been given a point on this line in a verbal description, but it's still a point nonetheless. The next part of the sentence does the same thing again, just with different values. It tells us after 74 minutes of calls, the remaining credit is $18.16. So that gives us a second point, 74, 18.16. And then they ask the question. So they give us the task that they want us to do. What is the remaining credit after 92 minutes of calls? So that 92 minutes of calls is again a value for x, and it's a known value for x, right? It's a specific number. And they're asking, when x has that value, what is the remaining credit? What is the value for y? So it's a known x value and an unknown y value. So if we can locate the coordinates of that mysterious point, where the x-coordinate is 92 and the y-coordinate is unknown, then we will have answered this question. So now let's map out our strategy. We've been given 2 points on a line, and we want to know the coordinates of a third. Right? We know the x-coordinate's 92, but we want to find the y-coordinate at that point. So how do we do it? Same strategy as before. First thing we want to do to find an equation for a line joining 2 points is to find the slope joining those two known points. Same way as always. Measure the rise by subtracting the y-coordinates, measure the run by subtracting the x-coordinates, and then divide those differences. Then we can use that slope to make an equation relating x and y together. And because we don't know an intercept, it's again probably easiest to use our point-slope form of this equation. Once we plug the slope and any point into that equation, then we'll have an equation we can then use to find the value for that third point. To do that, we just have to plug in the x value that we know, which is 92, to determine the y value that we don't. All right, let's get to it. Let's take our 2 points that we know from the statement of the problem and find the slope of this linear relationship. By subtracting the values of y, 18.16 minus 23.92 to measure the rise. If I subtract them in that order, I'll get negative 5.76. Subtracting the x values, 74 minus 38, will give me positive 36. So there's my run, which is the denominator of my slope. And I want to take a quick pause here, now that we have a fraction that looks like a slope for our relationship, and think about what that slope actually tells us about these calling cards. So because our vertical quantity here is remaining credit, the numerator of this slope, negative $5.76, is a change in that quantity. In other words, it's a reduction in the remaining credit of $5.76. Meanwhile, the denominator, because it measures calling time in minutes and it's positive 36, that corresponds to an increase in the amount of calling time by 36 minutes. So this fraction is telling us that if I decide to make a 36-minute call, when I increase the calling time on my card by 36 minutes, then the amount of credit left on that card is going to decrease because that numerator is negative, by $5.76. So that's a contextualization of this fraction, this quantity, this slope that we haven't yet simplified. I wanted to pause and talk about it now before we simplify this quantity, because that's really what it means about this calling card. Well, okay, what about after we simplify? If we punch this fraction into our calculator, if we do this division problem, we'll get negative 0.16 as the slope of this line. But remembering where the units of this slope came from, the numerator was dollars, the denominator were minutes. And therefore, this number, 0.16, has units of dollars divided by minutes, or dollars per minute, if you like. So what does that mean? This means that as I rack up more and more calling time on my card, the remaining credit on my card is going to decrease at a rate of 16 cents per minute. In other words, for every additional 1 minute, we could put a denominator of 1 underneath this if we wanted to, and think of it as 1 minute and negative $0.16. For every additional 1 minute of call that I make, the amount of credit on my card is going to go down by 16 cents. In other words, $0.16. So that's a contextualization of the slope of this line, which we're now going to think of as just negative 0.16. Great, so now we know the slope. Let's use that slope to find a point slope equation for our line. Y minus y1 equals m times the quantity x minus x1. M is our slope, negative 0.16. x1 and y1 are the coordinates of any point that we know. We can use either point. So just for kicks, I'm going to use the one where x is 74 and y is 18.16. So I'm going to plug that in for x1 and y1. Now let's just do a little simplifying. Distribute the negative 0.16 into the quantity on the right-hand side over the addition and end up with y minus 18.16 equals negative 0.16x plus 11.84. And then to get the y by itself, we just have to add 18.16 to both sides, giving me y equals negative 0.16x plus, turns out we get a nice round number, 30. So there's an equation in simplified fashion for this linear relationship between calling time in minutes, which is x, and remaining credit on our card in dollars, which is y. Y is equal to negative 0.16x plus 30. Great, but that wasn't the point of the story problem. The point of any story problem is not to get an equation and be done. The point is to then use that equation to determine something else. Again, what we really want to know in this problem is what is going to be the amount of credit remaining on this card if 92 minutes of calls were made, which has given us a value for x, namely x equals 92 minutes, which we can then plug into the equation to determine y. After all, that is the entire full purpose of having an equation in a story problem. An equation's job is to relate the values of two quantities together so that if we know one of them, we can then find the other. So plugging a 92 into this equation for x, and then simplifying, negative 0.16 times 92 is negative 14.72 plus 30, 15.28. So when x is 92, y is 15.28, and all we have to do now is remember that y represents the remaining credit on this card in dollars, so we better put a dollar sign around this answer. So after 92 minutes of calls were made on this card, we're going to have $15.28 of credit left. So in this big, scary story problem, the trickiest part was figuring out what was the nature of the information that was given to us. The first sentence in this paragraph told us that the credit remaining is a linear function of the total calling time, which means let's think of the credit remaining as our y variable and the total calling time as our x variable, and that those two variable quantities are related together by a linear equation. And we know what linear equations are supposed to look like. So then we looked at the rest of the information given and realized that it was giving us 2 points. It was giving us a point where x was 38 and y was 23.92, and then a second point where x was 74 and y was 18.16. Realizing that that's really what this problem is in essence, a problem where we're given the coordinates of 2 points and asked to find and subsequently use a linear equation which joins those 2 points, we now know what to do. Find the slope that joins those 2 points by dividing the rise, the vertical difference, by the run, the horizontal difference. In this example, that slope was either, we could see it as negative $5.76 divided by 36 minutes. In other words, if we make 36 more minutes of calls, we're going to lose $5.76 of credit. Or if we simplify that fraction, we get negative 0.16, meaning for every 1 minute of call that we make, we're going to lose 16 cents of the value of our card. Plugging that slope into the point slope form of an equation for a line, along with either of the 2 points that we know, and then simplifying, we find this fairly straightforward equation, y equals negative 0.16x plus 30, describes the relationship between these two quantities given in the problem. And then it's just a matter of using that relationship. Because we know what we're looking for is a situation where we've made 92 minutes of calls, so we know that x needs to equal 92. And the part we don't know is what's the value of y going to be, which we can find by substituting 92 for x into our equation and then simplifying to determine y, $15.28. So that's it for today's office hours. Thanks to those of you who contributed questions to the list today. I hope that this was useful. When we come back on Monday, we're going to be talking more about solutions of systems of linear equations. So contribute any questions that you run into over the weekend along the way, and I'll try and shed some more light on the various topics. So we're definitely going to look at how to solve equations using graphs, using substitution, and using elimination. And as time permits, I'd also have a couple of examples of how to use notation for functions, which is a topic that shows up at the end of Unit 3 as well. I hope you enjoy your weekend, and I hope to see you Monday morning at 9 a.m.